So neither of you have questions about the project? Okay, if anybody does, just again, email me whenever you want. It's due tonight. Let's see. So what I want to do today is we will talk a bit more about vortex methods, and then we will take a look at Fourier transforms. And Fourier transforms are used in a very special solution procedure called spectral methods, if you've heard of it before. Okay, so we will just take a look at how exactly these spectral methods work. Not in too much detail, just to get an idea. Okay, so let's see. Last time we had, with vortex methods, we had basically decided that we would solve the vorticity equation, which is very similar to the original momentum equation with slight differences. So d omega by dt equals, there's a vortex stretching term, which is 0 into d. Then there's the diffusion term, and that's it, right? So there's no pressure term, and the left side is, this is just, if you expand it out, it's d omega by dt plus u dot f omega. Okay, and so we also talked about that there's several advantages to using these vortex methods, right? So let's see, we can make a list of some of the advantages. So, the first one was that we don't have to deal with pressure boundary conditions. Right, so in the normal momentum equation, the pressure term is the most problematic term. Okay, so in vorticity form, we no longer have to deal with that. Another advantage is if we use semi-Lagrangian transport, for solving the advection split, the advection fractional step, which is basically d omega by dt, which is so if you use semi-Lagrangian methods to solve this term, what happens? What is the advantage? Do you remember? So if we were to use normal finite difference to do advection, what is the limitation that you have seen in terms of getting to the answer? Think in terms of the time step, right? So whenever we solve the diffusion equation, there is a time step restriction. When we solve an advection equation, there is also a time step restriction, the CFL condition. It turns out that with semi-Lagrangian transport, you have no restrictions on the time step for stability. Okay? But the solution, of course, will suffer if you decide to take very large time steps. The accuracy will suffer, but stability will not be an issue. These are two separate things, stability and accuracy. Okay. So the CFL, the stability condition respect to delta T no longer applies. Right? So there's no CFL condition. Right? But larger delta T's will reduce the accuracy of your solution. Okay. What are some other advantages that might show up? Think in terms of computing. When you look at a flow, what are you interested in? Which regions do you want to simulate? Do you want to simulate regions that have constant velocity, or you would rather simulate regions where things are happening, right? So where the velocity gradients are non-zero. So the vorticity field, omega, basically tells you where you should allocate more computational resources. So high omega values, omega magnitude implies we need more grid points. What about high velocity magnitude? So, I mean, it makes sense, right? When there's high flow velocity, we should also put more grid points. Is that true or not? Do you know what I mean? So if I look at a flow and I see very large vorticity values, I can say that, yeah, things are happening very fast and there's small length scales in space. So it makes sense that I would need maybe smaller delta T's and smaller delta X. What about high U? Any guesses? Yes, no, maybe?
I don't think it needs more grid points.
Okay, so you're saying no, we might not need more grid points. Why?
Simply because it's high doesn't mean that anything is changing and we have to concentrate there.
Yeah, exactly. So the magnitude is high doesn't mean things are changing in space. So if things are not changing in space, why waste resources there, right? So imagine that there's uniform flow coming in at 5 meters per second. Okay? This is a relatively high velocity. But there's no gradient at all. There's no du by dx, there's no du by dy. Nothing is changing. So it doesn't make sense to allocate a lot of grid points for this region. Okay. High magnitude of velocity, but does not require too many grid points. All right, now what I will do is I will put a rigid flat plate over here. What happens now? There's incoming flow by a flat plate. Do you have a rough idea of what the flow will look like over the flat plate? You know, just as a, you know, I want to make a schematic. What should I draw?
boundary layers on both sides.
All right, there will be boundary layers on both sides. Why?
Because on the surface of the plate, the velocity will be 0.
Yeah, on the surface of the plate, the velocity of any fluid particle has to be 0. And then slowly it will increase up until it matches the u infinity. Right? U infinity here is 5 meters per second. So you get a profile, velocity profile that might look like this. On the other side, it's this exact opposite profile. Right? Yeah? And vorticity on top is plus or minus. Does the question make sense? On top, will you have positive vorticity or negative vorticity? So don't think in terms of formulas and computing. Just think in terms of what vorticity represents. It represents the direction that the fluid is rotating. Right? It's rotating anti-clockwise, positive.
So it's counterclockwise. I think.
Always? In this case?
On the top of the.
Okay. So on top, it's counterclockwise. Why do you say that?
Intuitively, I think.
Yeah, so if you just put a stick in the flow on top of the plate, the stick will start rotating this way, right? Because this part is going faster and this part is going slower. So yeah, you're correct that omega on top is positive. Positive, negative, yeah. And omega on bottom with the same logic is negative. Of course, I mean, when you put a small stick in there, the flow will change slightly, but overall, what it will do is it will start turning this way. It will start turning clockwise on top. What did I say negative? So this is minus, and this is negative on top, positive on the bottom. Okay, so, but now you see, because of the wall, things start changing. The velocity starts changing, at least in the y direction. Okay, and now we can argue that things are changing very fast close to the wall. We should put down more grid points right at the wall, and that's exactly what computations do. Close to the wall, you concentrate as many grid points as you can, and as you go farther, you smooth it out slowly so that you can use larger cells. The reason for doing this is, again, saving time for your computation. You're free to use very small cells everywhere, but then the number of cells you will end up with might be 10 times larger, and if you use this sort of stretching. Okay, so if we solve the vorticity equation, we never solve, well, we do solve for u, but we work mainly with omega. And omega directly tells us that, yeah, these are regions where you need to put down more points. Or these are regions where you have too many points and get rid of some and save some computation. Okay, make sense? All right. Now, let me write down something before I forget. Okay, I will remember. So this argument of, okay, when gradients are, for larger gradients, we need smaller grid size. It might not be intuitive right away, but we can draw a very simple profile and take a look at how delta x affects the solution. So let's draw a very smooth profile, right? And let me discretize it like so. Okay, so my grid points are actually the triangles I've shown you. And in computation, that's the handicap we have. We never know what the function itself looks like. We only know what the xy coordinates of point number 1, point number 2, 3, and 4 are. And we have to sort of, have an approximation for what we want to do, how we want to represent the function that's in the background, the black line. Okay? So we might say we will fit parabolas in between each of the points. And this is a completely separate, huge numerical field. What is the best way of using smaller functions in between points so as to represent my full curve as accurately as you can? What's the simplest thing you can do? I give you the triangles and tell you, draw me the curve. What would you do? The simplest thing.
With straight lines through.
Yeah, you would join the points with straight lines. Right? You would do this, and that, and that. All right? So our approximation with the blue segments is very close to the actual black curve. And that happens because things change slowly. Okay? So let's see. Approximation resembles actual function. And the approximation is discretized approximation. Actual function quite well. Reason is the function changes slowly. Okay. Or in other words, the gradients are small. Okay, now, but if we say that, okay, my points are somewhat similar. But my actual function, the true function actually looks like that. What is the approximation that we will get? Again, if we start joining straight lines, we will get a straight line that's perfect, and then we will get a terrible approximation. Okay, so here, the approximate reconstruction is does not resemble the actual function. And here, the reason is the gradients are large. The gradient is large. Okay, so what should we do to make sure that we approximate the actual function well? One thing you can do is you can say, oh, no, I will not use straight lines. I will switch to cubics. So I will fit a cubic in between each point. It involves more computation. You have to take care of including more points from both sides, left and right. that's doable. But again, at some point, this very sharp gradient will give you trouble. Okay. So instead of doing fancy things, what is the simplest thing you would do?
More points?
Yeah, you would put down more points. So instead of using 1, 2, 3, 4, let's put down a lot more. Let's say 1, 2. Okay, and let me recreate that. So again, the black line is the actual, and more points are just, I'm using more discretization. Okay, maybe not that. Okay, and now you can stick to your linear approximations in between. And you will, the only problem you will have is again when the gradient changes very quickly. But you can see it's already much better than the older approximation. Okay? So, you know, that's exactly why vorticity is very useful. Because vorticity basically is that black cross tube, right? So it's computed using velocity gradient. Gradients of velocity and hence omega large implies we should use 4 points. Okay. And as you mentioned, this is not the case with U large. U large might just be uniform. You only care about changes in space and in time. All right, so, you know, so vortex methods are amazing. They're awesome. Everybody should use them. True or false?
False.
Why? Why false?
Because
We've only been talking about advantages. Can you think of a disadvantage? Especially think in terms of this flat plate, right? We've introduced a wall. What happens to vorticity?
I think that initially the boundary conditions was one of the disadvantages, for example.
Yeah, go on.
For example, we don't know what is the what happens in the boundaries.
Yeah, you're exactly right. With U velocity, we know what should happen at the wall. It should be 0, or it should move with the wall. Right? With vorticity, that's the biggest problem. We know that omega will not be 0 at the wall. You can see that here. Du by dy is already non-zero. So it will be some non-zero value, but we don't know what. We don't know what value to set the omega wall to. Okay? So that's the biggest disadvantage. Every method has its own pros and cons. Every method. You just have to decide what works best for your problem. Okay. So disadvantage. It's omega wall is not 0 in general and must be computed at every time step. Can you think of some ways to compute omega wall? Have you heard of panel methods before? No? So, do you remember, okay, you've heard of potential flow, right? Point vortices, sources, sinks, doublets, etc. So, the idea in panel methods, before we had nice computers, when early on people were saying, okay, we can approximate real flows, very high Reynolds number flows as potential flows, which is a bad approximation. But they were working with what they had, and the way you can represent a body in a flow, for instance, the cylinder was the simplest example. Okay? What you would do is you would introduce a source and a sink. Okay, a doublet basically. So introduce a doublet with appropriate strength. And this gives you potential flow over a cylinder. Okay, and the same way you can introduce sources and sinks inside an airfoil to make the flow behave as if there's an impenetrable boundary that resembles the shape of the airfoil. Have you heard of D'Alembert's paradox?
Just here. Forgot.
Once more?
Yes, that was because of the pressure side and the suction side.
You're talking about how airfoils work usually. But in potential flow, D'Alembert's paradox is related to the airfoil, exactly. Do you remember what it says?
I forgot.
Does anybody else remember? Okay, so D'Alembert's paradox was the airfoil does not generate any lift in potential flow. Now, of course, this we know, for real airfoils is not true. The airfoils will generate some lift. And then, people were trying to fix this mathematical problem, and then there was the Coulthard condition, which said that flow should stagnate where? Have you heard of this before? No? Okay, so he basically said that flow should stagnate at the trailing edge. Not allowed to turn around. Okay, so before you apply the Coulthard condition, the flow might look very strange at the trailing edge. Let me use a different color. It might do very strange things. And again, I'm drawing a sort of a schematic. And what Coulthard condition does is, it does not allow any non-zero velocity at this point. So what that does is, in the end, the streamlines now behave as they should. Okay? And they realized that to enforce this, they had to introduce circulation on the airfoil. They had to add a non-zero circulation. Okay. And this circulation now gives the correct prediction for lift. Correct to some extent. So this was a major breakthrough that, okay, when you impose the condition, that is, you don't allow the flow to move at the trailing edge, the flow behaves as it should. And this can be done by introducing, in addition to the sources and sinks, introducing some way to generate circulation, which basically corrects the flow. Okay? And this circulation gives you the correct value for lift generated by the flow. Okay, so that's when panel method started. How can you do this? You can do this by actually laying out a sheet of vortices on the surface of the body. Okay, a sheet of point vortices. Each of them has some omega or gamma. Gamma is the strength. Gamma 1, this might be negative, gamma 2, gamma 3, right? And so on. Each of them are independently rotating point vortices. And this was the mechanism to introduce circulation. Okay. And so all the gammas, the gamma i's are unknown initially. And gamma is the vortex, right? And they are computed using the, how should I say, the desired outcome, the desired, let's say, desired boundary condition. Okay, so for the time being, it might still be a little abstract to you, but let's talk in terms of cylinder, okay, where there's no issue of generating lift. Oh, sorry. Okay, let's see. Before that, okay, if we have a bunch of 3-point vortices, distributed in space, as follows. Let's see, this is a point vortex with, let's say, gamma 1 equal 10. This is another point vortex with gamma 2 equal -4. Another point vortex with gamma 3 equal 5. And I want to figure out the velocity induced by these point vortices at this location. Okay, at this location, I want to figure out what is the u and v that these individual vortices induce. Okay. So does that make sense, what we're trying to do? And in potential flows, there is a formula for this. Okay. If you know your current xy coordinate, if you know your strength, no matter where you are, if you give me the radial distance, we can figure out what the velocity magnitude is. And yeah, I mean, that basically gives us the u and v components. So if we look at a single point vortex, it will, let's say omega is 5 radians per second. We go out 1 meter, velocity will be Alright, okay, so the question is, if we have a point vortex with, let's say, omega equals 5 radians per second, if we start moving away from the center of the vortex, 1 meter, let's say, what is the velocity at this location?
In potential fluid?
In general,
Superposition of the.
let's only talk about a single point vortex. Okay. Or if you prefer, think in terms of a rotating solid. The solid is rotating about the center here, and omega is constant. Omega is, let's say, 2 pi radians per second.
Omega times the distance.
Yeah, exactly. It's omega times how far away I am from the center. Okay. If I'm 1 meter away, it's 2 pi meters per second. If I'm 2 meters away, omega does not change, but velocity doubles. So the same thing happens here. Actually, not the same thing, but the same idea applies here. Depending on how far away we go from the vortex, the velocity can be determined. And the farther away you go, the weaker the effect of the vortex. Okay? So because of this vortex, the velocity, induced velocity will look something like this. Okay? It's always in the radial direction. Because of this vortex, the velocity will look something like this. Okay? Because of this vortex, let's see, we are radially this way. Okay, so the velocity will look something like this. Okay. And all of these individual components you add together, you get your final U and V. Does this make sense? So, if I introduce more point vortices, each of them will have their own velocity, induced velocity at this location. And we just sum them all up. Okay. So the same exact idea applies when we talk about the boundary. Let's take a cylinder. We have the cylinder and we lay down these point vortices whose strength is to be determined. Okay, so they are again point vortices with different gamma values. And all around the flow, what do I have in vortex methods? When we solve the flow around this with vortex methods, what do I know around outside the cylinder? So this is a solid, outside is fluid.
Vorticity.
You know vorticity at each grid point, right? So if these are fluid grid points, I know vorticity at each of these locations. And now, each of them has their own gamma, which is known. And I know that the total velocity that these orange vortices and the black vortices, the sheet that I laid out, the induced velocity on the surface should be 0 because no slip and no through flow. Assuming the cylinder is not moving. If it's rotating, if it's moving, the velocity on the surface should be that velocity. Okay. So, all right, now that's basically what we do. So we lay down the sheet. One is lay down sheet on surface with unknown strengths, gamma. Two is we know U on surface should be equal to 0, assuming cylinder is static. Okay, we can determine that we can determine the unknown gamma I values such that the combined induced velocity on the cylinder surface. Due to both gamma i's and omega fluid is equal to 0. Okay, and this gives us a system of equations from where we can determine the gamma i's. Does it make sense? It's also called the boundary element method. There are many variations, but this is the basic idea. Any time you use vortex methods, the wall vorticity is non-zero and has to be found. And the way you find it is by putting down this sheet of vortices, point vortices, that combined with the fluid vortex points ensure that no flow moves into the cylinder or there's no slip on the surface of the cylinder. Make sense? Okay. So yeah, I mean, people have researched this. It was a very active topic of research in the 1990s, and they came up with several ways of doing these things. But the basic concept is this. All right, this seems like a big issue, right? You know, here already we have a curved geometry, and we have to lay down the points, and you know, this does not match the grid. And if this geometry starts changing in time, imagine a fish, and it starts undulating in time, you know, things become much more complicated. Can you think of an alternative way of doing this instead of laying down this nice vortex sheet? Yeah.
So we can start with some omega value at the boundary, at the wall, and then we know the velocity. We will be knowing the velocity at the first grid point, just above and below the wall, and using that we can evaluate vorticity at every time at the wall.
Yeah, that's true, but it's similar to the concept we talked about here, right? You know vorticity right up or at a point right above the wall, and then you put down some value of omega, so the through flow and slip velocity cancel out. That's what you mean, or not?
No, I mean, if we don't use these omega I values, instead we totally rely on the velocities computed by our simulations.
But wait, how, okay. Can you explain a bit more? How do you mean?
So we can start with some random guess for omega at the wall in the beginning, and then we will, at the next time step, we will have some solution, and we will have a velocity solution using that inverse formula we derived in the last class.
Okay.
And then we know the velocity just above the wall and just below the wall, and so using finite difference.
Okay. All right, wait 1 second. Yeah. So you're saying take some random values for these omega walls, correct? And then solve one step. You get some velocity on top, and then you enforce that the velocity on the boundary should be 0, right?
Yeah, and evaluate the vorticity at the wall accordingly for the next time step.
You're assuming that the vorticity above the wall you have computed using this random arrangement is correct, which is not true. Make sense? No. If you generate a random distribution of omega here, you will get some resulting u outside. But this u is not correct. It's
but this can be the transient, and as I progress in the solution, it can converge to
iteratively. So you have some wrong guess, and then you keep then you update your omega wall again. How do you update your omega wall with this wrong guess of u outside? That's what you have to do, right?
Yes.
So it's the same idea. You have to keep updating your omega wall until you get to the correct no slip,
Yes, yes.
no through flow condition. So conceptually, it's similar to what we talked about. You do need to keep computing omega wall. You can for sure do it iteratively. Yeah, that's a valid way of doing this. But there's no escaping this. Okay.
Okay.
Also, if you're looking at unsteady flow, we would have to do this sub-iteration you're talking about maybe 10 times, 20 times, every time step. Going from time step n to n plus 1, you might have to do several iterations until you get the correct boundary condition. Yeah, but again, that's a valid way of thinking. So, but again, that involves computing omega wall and updating it until boundary condition is satisfied. The simpler way of doing this is using penalty. Do you remember? We talked about ring penalization. Do you remember the name? Penalty method? All right, so let me just recap quickly. So, penalty term in the momentum equation. So let's see, we had du by dt plus u lambda u equal minus lambda t by rho u lambda squared u plus some forcing term, right? And this forcing term looked as there was a lambda, there was a chi, there was a u solid minus u grid. Okay, and if you remember, what we do is we have the grid and any cell that is occupied by a solid gets this value chi equal 1, and outside we have chi equal 0. And this is called the characteristic function. Okay, and if you remember what the term is doing, do you remember what the term is doing? So we have the normal Navier-Stokes and this extra term, and this extra term is doing something special. No. So does this make sense? What chi is? Lambda is a constant. Let's say it's a constant. I will give you. Okay. So suppose our cylinder is, the grid we put down goes inside the cylinder and it's outside. Anything that's inside gets a value of chi equal 1, this value. Anything that's outside gets chi equal 0. So when we are in pure fluid, this term goes away. We have the pure Navier-Stokes equation. Only inside grid nodes that are occupied by the solid is this term active. Okay. And anytime my U inside does not match the U solid, which is the boundary condition we're trying to impose. Boundary condition is the condition inside the solid. Everything inside should move with the solid. So if there is a difference, this term becomes active. If the velocity inside that we computed with, say, fractional steps is smaller than solid, this will cause that fluid packet to accelerate until it catches up. And if it's faster, it will cause it to decelerate till again it catches up or slows down. Make sense? Fine. This is in velocity. How do we go to vorticity? How should we modify this term to make it work with vortex methods?
I think the same way that we develop curl of the both sides.
Yeah.
So curl of
You can take nabla across the whole thing.
nabla cross.
Curl off the whole thing. So this, everything from here becomes the vorticity equation, and we have an extra term. So we have del omega by del t plus u dot lambda u lambda omega plus what?
Plus lambda k kappa k omega s minus.
See, chi can vary in space, right? So there's a variation of chi in space. So nabla cross chi, we cannot pull chi up. It's not necessarily a constant. Okay? So we leave it inside to be learned. In implementation, you will see there's not much of a difference whether you pull chi out or not. But mathematically, we can leave it out. So we just have nabla cross the term inside, which is chi us minus u. That's it. You're done. Your no slip, no true flow boundary condition is imposed inside the solid. Okay. And yeah, some of the simulations I showed you use this exact equation. How do we solve this equation? Anytime we have a huge equation, what do?
Splitting.
We split it, all right? So, first we can do the penalty term, C, which becomes del omega by del t equal lambda nabla cross chi u s minus u. What is known here? What is unknown?
U is unknown, right?
This u is unknown. This us, is it known or unknown?
That is unknown as well.
So us represents what? Us represents, let's say,
Moving of solid, the cylinder.
yeah.
You got it. So it's stationary. So.
Yeah, so if you have a solid cylinder that's stationary, this is 0. If you have a solid cylinder that you hold on a stick and you start moving, this will be some ux value, constant ux value. If you start rotating the cylinder, you compute this with ux plus omega cross r. And if you have a fish that's deforming, this is translation plus rotation plus deformation. Okay? So this is what you impose. Imposed by us. Okay?
What if we are not enforcing the velocity on the solid?
Give me a case when that would be true.
A floating cylinder, freely floating cylinder.
Yeah, that's a good point. So if you have a tank and you have a freely floating cylinder, let's say made of foam, and you start the flow, the foam will get effective with the flow, right? So you don't actually change anything in here. What you need to do is you need to figure out what the u velocity of the cylinder is at the current time, okay? And that you do by, solving each of these things, and at the very um, end of the split, you can compute the forces on the cylinder, okay?
Okay,
The
so
X force and the Y force. Once you know that, you know how much it should move.
okay, so use the previous time step.
Yeah, exactly. So if it's a freely floating cylinder, you compute the forces on the cylinder from the previous time step. That gives you its u equals that. Okay, and this u is computed. How is it computed? We're solving the omega equation, so you don't have the u, right? So we can compute this from the omega at previous time step. Using a, what was it, lambda squared u equal minus lambda cross omega n. Okay, that's the first split. What do you want me to do next? So let's say the output of this is omega star. Okay, what should I do next?
Advection.
Next term.
What sort?
You split it, right? Next term, or
Okay, so you said I should do advection. What should I do? What do you say?
I said doing for the next term of the equation.
Which one do you want it to be?
U nabla omega.
This one? U dot lambda over. All right, so I guess you're in agreement. We do advection. So we will do d capital omega star by dt equal did I confuse? Equal 0, right? This is the advection. When you expand it out, it's just d omega by dt plus u dot lambda. And this you can do with semi-Lagrangian transport, or you can use finite difference as you wish. Next, we can do diffusion. Okay, so let's say the output here is omega star star. Next, you can do diffusion d omega star star d no partial equal nu omega. Okay, slow down. Omega star star. Okay, and the output here can be 3 stars, and you can do the vortex stretching term, or if you're in 2D, you don't do that. But at the very end, what you do is you have to recover the vorticity. Okay, recover the velocity. And okay, so let's zoom into D. No vortex stretching term. let's say the output here is omega n plus 1. So we're basically done here. Omega is n plus 1. Recover vorticity using the formula lambda squared u and n equal minus lambda cross omega n plus n. Sorry. What am I doing here? Okay, n plus 1 and n. Okay, and when you go to the next time step, this un plus 1 goes in here. Or the n plus 2n times. Everything makes sense? So, yeah, we haven't done anything very fancy. We just said, okay, we will let our penalty term stay in the momentum equation. We take the curve, which gives us this extra forcing term in terms of vorticity. Then we split. We do the penalty first, then we do advection, or if you prefer, you do diffusion here, and advection here. And at the very end, we recover for velocity, which we will use at the next step, over here and in advection. Everything makes sense? Okay, so that's basically all of vortex methods. Made it easy using breakdown penalization. Okay, do you have any questions at this point before we go on?
I still have a problem with the penalty method, basically.
Go ahead.
For example, US, when US is 0,
Yeah.
means solid is not moving. We added a term that is U times lambda kappa. So
Yeah, so think of this
I have
in
a-
terms of, this is your solid which is not moving, correct?
yes,
You put down your computational grid all over the place. Okay? Grid points are outside, grid points are inside. Since the solid is not moving, what should the velocity at the grid point inside the solid be?
the fluid or
What should the grid point of this,
0 is
it should be 0, correct?
yes.
But when we solve advection, diffusion, pressure projection, we assume that the solid is not there. That's what we do in penalty method. So this will introduce an error, which is corrected.
So it's subtracted from the
Yeah, so any difference between what we want it to be and what it's not, will force it to be what it wants.
And when it is moving with the same velocity at the, for example, the solid is moving the same velocity as u, that term should disappear.
Yeah, this term will be 0, because then the solution inside is correct. You don't want to change it. Okay? In penalty method, you just get rid of the solid, pretend it's not there, do your solving, and then you correct it. Okay? And any method has to do this. Whenever you split, you have to solve until you reach a correction point. Whether you use inverse boundaries, whether you use omega wall, they're also correcting the velocity to make sure it doesn't flow through the walls. Right? So it's the same idea. Is that good?
Yes.
Anything else? Okay, so we have 15 minutes. So let's see. Okay. Okay, I will do the Fourier transforms next class, but I want to tell you about some terrible methods for solving the cosine equation. Okay, on condition that you promise never to use them. So this is good for you to know, because in case somebody says, "Well, why don't you use this method?" So you can say, "This is the reason why." So some terrible methods for solving AX equals B, alright? Okay, so Jacobi iterations. Gauss-Seidel. SOR is successive over relaxation. Okay, so these are all very fancy sounding names. They impressed me when I was learning these, and then when I actually learned these, I was like, "What? You're kidding me!" So. Okay, so if we go to the definition of let's see, we have the Jacobi method here, right? All right, so there's an AX equals B, there's very impressive looking equations, and there's the final answer, okay? But when you actually start implementing this, all it does is the following. Let's say we have a system, I will create a fake system. Let's say we have 3x plus 5y minus 7z equal 13, 2x minus 8y plus 9z equal 27, 10x plus 27y minus 13z equal 5. Okay? So I've just written some random system of equations, and you can solve this very easily. Okay? So what does Jacobi iteration do? Have you heard these before? Jacobi, Gauss-Seidel, and so on? Okay, yes, no. All right. So Jacobi just says, all right, I have my three equations. I want three unknown variables. So let me rewrite them as, what is this? This is 13 minus 5. Let's say x at iteration number 1 is minus 5. Y at 0 plus 7, z at 0 divided by 3. Okay? So I've just taken things to the right hand side, except the variable I'm interested in. Then y1 will come from the second equation, which is 27 minus 2x at 0 plus 8y at 0 over minus 8. And the same for z. Z at 1 equals 5 minus 10x at 0 minus 27y at 0 over minus 13. Fine. So x, y, z can be computed as follows. What are x naught, y naught, z naught? Since you've seen this before, do you remember? How should I pick x0, y0, z0?
I think they are initial guesses.
They are initial random guesses. You can pick it to be whatever you want. Okay? So, where we pick the x0, y0, z0 arbitrarily. Okay? So you pick x0, y0, z0 arbitrarily, plug it in, you get some values of x1, y1, z1. Then you use this x1, y1, z1 to compute x2, y2, z2. We're iterating. We compute x1, y1, z1, and keep going with the iterations until the values don't change anymore. Okay, so what would x2 be? x2 is, we just take the same equation, 13 minus 5y1 plus 7z1 over 3. y2 is, again, the same thing we wrote before, but with x1s and z1s. Okay, so there's nothing here. And then people write all of this. Okay. All right, so what about the other fancy sounding names? Is the idea good? You start with random guesses and you keep computing the new values iteratively until it stops changing. This is a terrible method. You're not guaranteed that the answer will converge. If it does converge, it converges very, very, very slowly. Fine. Okay. Terrible method number 2, Gauss-Seidel. What do we do? Do you remember?
When we calculate the new x, we put that while calculating the new y.
Yeah. So, we do something similar as here. But, we've already computed x1. Why not use this x1 over here instead of this old value? All right? That is Gauss-Seidel. Done. That's it. Okay? So Gauss-Seidel is use updated values in Jacobi as soon as they become available. Okay, so you would say x1 is 13 minus 5y0 plus 7z0 over 3. But now y1 uses this 27 minus 2x1, not x0 anymore, plus oh, did I write 8y? Sorry, 8y. So there's one problem here. Minus 9z. Okay, so minus 9, what? Z1 or Z0?
0.
What?
0.
0, yeah, because Z1 we have not computed. Okay? So things that are available we use, otherwise we use core values. And so on. That's it. That's Gauss-Seidel. Okay? I will show you the Wikipedia page on that. But let's do the third one. SOR, successive over-relaxation. Do you know what this is? What is it?
Put a factor.
Put a weighting factor. Put a weighting factor for Gauss-Seidel updates. So if we say we want x1, we would say it's some 1 minus alpha of x0 plus this update, 13 minus 5 y0 plus 7z0 over 3 times alpha. Okay? So, yeah. If you set alpha equal 1, this term goes away, and this is just normal Gauss-Seidel. And y1 is 1 minus alpha of y0 plus 27 minus 2 x1 minus 9 z0 over minus 8 of alpha, and so on. That's it. That's successive over relaxation. Alpha equal 1 gives us Gauss-Seidel.
I think there's under relaxation too, right?
Yeah, under relaxation, successive over relaxation, successive under relaxation. Under relaxation, your term, wait, I've forgotten. I have to check, but think you use a negative in, yeah, I will check before I tell you. Yeah, there's nothing different from SOR. I think there's just negative signs. Okay? So yeah, these are, again, fancy sounding names. There's nothing in here, absolutely nothing. You know much better methods already. You know how to solve AX equals B by forming the matrix or by doing pseudo prime iterations. Those are good methods. Do not use these ever. Why are they used at all, or why are they mentioned at all? When I was learning parallel computing, that's when I first came across these. So if you see Jacobi, X, Y, Z can be computed completely independently. You don't need to know X1 to compute Y1 or Z1. So it was a good toy problem for parallelizing. People will say, yeah, Jacobi you can parallelize. But then, you know, Gauss-Seidel and SOR are slightly better than Jacobi. And then here people would say, but these you cannot parallelize. See, there's an X1, which must be computed before I can go to Y1. So everything is sequential. Okay? So yeah, it was a good exercise, but never use these in practice. Okay. Technically, you could use these in when we solve pi minus 1 plus minus 2 pi plus pi plus 1 over delta x squared equal f of xi, right? Instead of forming the ax equals b matrix, this is all n plus 1. Instead of forming the ax equals b matrix, you could just say pi at n plus 1 is equal to f of xi minus pi over minus 2 minus 1 and plus 1 plus pi minus pi plus 1. Right? And although these are unknowns, I will take initial guesses and keep iterating. Yeah, you can do that. You might converge, you might not converge, you might converge to the wrong answer. Anything's gonna happen. Okay? Go ahead.
Time is up.
Okay, so we can stop.